Hello, in this video I was going to share my progress so far trying to make a non-invasive glucometer. So a glucometer to measure the blood glucose levels without actually drawing blood from the finger. And this one's using optical sensors. Before I get into it, a little disclaimer. I'm not a medical doctor, I'm not a doctor, I'm not a medical researcher, and I actually know very little about diabetes. This is completely from the standpoint of hobby electronics. So just take it with a big grain of salt and understand that this is really tinkering, not professional research or commercial research. So that's just my disclaimer. But I'm just going to go ahead and get into it. I put some slides together to sort of talk about the progress and the limitations I've had so far with it. And then I think that after I go through the slides at the very end, I will sort of show you how I've been using it. Bottom line up front, this does not predict blood glucose levels right now. I'll get into the details on it. If you just want to see for yourself the documentation, don't really want to watch the video, this is where I have all the information on this as I've been working on it. So if you want to skip the video and just get down to the details, go check out that link there. Otherwise, you can just sort of sit back and I'll share the updates and sort of the lessons learned so far with it. Okay. So yeah. So it's non-invasive glucometer. Progress so far. The first sensor is built. It's all put together here. It logs data from 4 phototransistors, so 2 on this side and 2 on this side, at a rate of 300 hertz. Everything is documented to recreate this sensor, and it's available on GitHub at this location right here. That includes your electrical schematics, your STL files, your parts list, your source code. Everything's on there. So you should be able to recreate this from what's on GitHub. And it's all covered by the MIT license. It's free for reuse, commercial use, otherwise. So very open license. You can basically do whatever you want with the information. Use it however you like. So that's the big progress. The major limitations or cons. It doesn't actually predict. There's no built-in prediction of the blood glucose level yet. Everything that I've been doing so far is in post-processing after I've logged the data and MATLAB or other scripts. The wiring is a little inconvenient for sure. You can see that this is, it's not super easy. It's a little bit of a mess there, so it's not trivial. Not super easy to reproduce, like just buying COTS parts. I'm limited to about 21 kilobytes of data before needing to interrupt the write to the SD card, so I have to write things in 21 kilobyte bursts as far as how I write to the SD card and record data. Limited data so far. This is a big one right now. I've only been able to test it on myself, so limited data so far, and accuracy of the blood-based glucometer I'm using is not quite as high as I sort of guessed it would be. And also, there's a contest at this GitHub page. Go check it out. You can win money if you're interested in making one of these things. Making a sensor yourself. You can, I think, the first place I put 1,000, second place 500, and third place $250. So you can make money, and yeah, if you want to give it a shot, and I hope you do. I would love to see some other people working on this as well. There's a bunch of rules in it. I'm sorry, it's sort of an engineering thing. If y'all are interested and you just think the rules are too much, let me know. Ping me. Send me a message, okay? I'm flexible. Yeah. So key takeaways for any sensor, some of the lessons learned. Consider where you're going to get your data. If you're doing the design experiment on your own, you're going to have very limited data. That's what I'm finding with myself. You're not going to have a wide range in glucose readings that are needed to evaluate the sensor accuracy. And just by having one person, you've got the issue of finger size, skin color, individual blood glucose, and heart rates are all going to bias the algorithms you come up with. So that is a real question, and I don't have a great solution for it yet. If y'all have ideas, feel free to ping me. But basically, you need a variety of people to get the data to test a new sensor. You need a variety of people with a variety of blood glucose levels. You're basically making a cheap portable oscilloscope that logs data. So if you're working in a lab, maybe it's commercial research or something like that, and you're going to have people coming to you, I'd recommend just using a high quality like oscilloscope to record the data, and you don't need to reinvent the wheel. You don't need to make something new. If you're going to have people coming to you, probably a nice oscilloscope is the way to test out your sensor and just connect that and log your data. If you have to send it out to people and you're looking into, I would look into like portable oscilloscopes that are already made, maybe commercially, or things people have already made with microcontrollers. And so you can avoid like the surprises I had with the limited RAM size for the amount of data I can write, and also some issues with noise during SD writing. So I can't try to intermittently write to the SD card certain like 512 chunks to the card while reading. And consider COT sensors. So this is actually really, really simple wiring. You can see the wiring diagram on GitHub. It's very simple, but even this simple wiring takes a while to sort of figure out what resistor values you need for getting the being able to read like the pulse on this the sensor, and it's just time consuming. So if I were to do it again, I might spend a little more time looking at what COT sensors are available, and that would probably speed up your start time. I spent a long time just adjusting these resistor values on a breadboard to get those things worked out. So if you're starting new, I would try to see if you can find something COTS first and save yourself some trouble. There are advantages to what I did too, but you know, pros and cons. Some of the key takeaways specific to this example sensor I have right here. What I've seen is that the finger matters in the correlation results. So what this says to me, and when I mean finger, whether I'm using my index finger or my pinky finger, and you can see that there's slightly different ways it clamps on there. You can see how far it goes down. So it likely means that the sensors are not flexible enough to different finger sizes. I'm not doing any detrend automatically on the data, which would also probably help a good bit with the finger size issue. Strong PPG signal is only seen when the IR LEDs are on, regardless of the phototransistor. So even though the PPG signal is observable looking at the data, the correlations with blood glucose do not vary strongly based off the LEDs being off or on. The LEDs I have in here, I have two LEDs down at the bottom here. One is infrared and one is red, or near infrared, 640 and I think 940 nanometers. So the key PPG features are not currently getting extracted. There's no like feature extraction on those. For the very first testing, I've just done like a mean of the signal during the specific interval that I recorded. So for the most part, the very detailed information on the pulse is being lost the way I've analyzed it so far. The strongest correlation, still very weak, is with the IR LEDs on, using the IR phototransistor with transmittance. So the strongest correlation has been with the infrared light going through the finger to the infrared receiver, or with both lights on, so the red and the infrared. Because the IR transmittant value does not shift significantly based on which LEDs are on, I'm not sure that the correlation is not just a coincidence. So I can't say for a fact that you wouldn't be able to recreate it with other data, or I don't know for sure that it's an actual correlation yet. It's still very weak. And detrending the data and applying moving averages improve the correlations. And that's not in real time, that's in post-processing. But there may be movement causing additional noise, spikes, and outliers in the data. And one way to solve that is you could integrate like an accelerometer and record the movement going on, and use that to filter or adjust to compensate for it. They do that, I believe, with, I can't remember if it's a pulse sensor or an O2 sensor. It's very, very common, but I can't remember the name offhand. But there are COT sensors out there that do that already. Right. Here's an example of some of the data from the logs, and all the logs are on GitHub too. So if you want to check it out, feel free to go look there. So here you can sort of see, and I'll try to get you a decent view. This is like one recording. So if I make one new log, this is basically the data I'm getting. Down here on the bottom is the time scale. Here are going to be the 4 different readings based on which LEDs are on. So we have neither LED on, the infrared LED on, both LEDs on, and the visible light on. And that's the same for each of these going in series like that. And then we have, this is going to be the phototransistor on the reflectance side, the red one. So that's going to be the visible light one right there. This is going to be transmittance for the red one, so that sort of white clear one right there. And then this is the infrared one on the reflectance side, so that'll be this guy right here. And then transmittance infrared, so that guy right there. And you can see how the readings are slightly different, but you can clearly see, you know, there is the pulse showing up in these signals. Pretty noisy there, but you can see a pulse showing up in these when we have the LEDs on. So that's what I mean by you can see the pulse with the LEDs on, but it doesn't translate to a strong correlation with the blood glucose levels, just taking the mean of these, which sort of makes sense. There are papers that do feature extraction on these pulses, and they've had good results. So, yeah. Yeah, all this is online. You can look at it closer if you're interested. But yeah, that's the big picture overview of what I get in each log. So here we can look closer at a single log too. This is, let's see, record raw data and access filters and post-processing. So this is log 13. We're looking at 940 nanometer transmittance, both LEDs on, person 1, that's me, using my index finger, recording at 300 hertz. So this is what it records in that little session. That's the raw log data at 300 hertz. And then this is just an example of how we can filter it and clean it up in post-processing. I've been using MATLAB, the signal processing toolkit. I've just been using their trial version to sort of play around and tinker with it. I'm thinking in the long run, I'm probably going to go to Python because it's free and it's free for everybody and it's easier to recreate. But MATLAB's really nice to get started, and they just make things so easy to get started. That's why I went with that first. But that's just an example of how you can clean the data up and apply those D-trends to it. Yeah, and this is something else I thought was interesting that I wanted to talk about a little bit too. So I have, and I haven't shown all the details on the correlations in this, because I don't think there's enough data to draw any super strong conclusions from them right now. I think I need more data to draw conclusions on how well the sensor is or is not working. But I did want to point something out that I learned about while doing this, which is, you can see here, this is called Clark's error grid analysis. And this is a method for sort of assessing the accuracy of a glucometer. And this is an example one right here. Some people were doing some research with, and this is an example using the one I've got here and predicting values in post-processing. And one of the things I wanted to point out is that there is this, what is this, mean absolute relative difference, and then root mean square error. So these are common calculations you'll see to describe the accuracy of a glucometer. And they also may include what percentage of it is in zone A in this Clark's error grid analysis chart. And if we were to just look at these two values, like this value compared to this value, this glucometer looks like, oh, this is actually a very accurate glucometer, or a reasonably accurate glucometer that you could use to make reliable, I guess, medical decisions. But it's not really true. When you only look at these values, it can be misleading, and that's sort of what I wanted to point out here, which is, you'll notice here in this one, glucometer A, that they have data going all the way up the spectrum from from about 100 to 400 milligrams per deciliter. So they have data points going all the way up. And you can see with me, I'm just testing with myself, so I've really only got values between about 95 and 135 milligrams per deciliter. And so I have a very narrow region here, and I did some filtering on it on this data, and then I did a linear regression to get a second order polynomial equation to sort of use as a prediction algorithm. And there was some other people that did that. That I think that if you look up YouTube videos of non-invasive glucometers, there's a video of some people with a very, like, I think they're also using like a microcontroller with an Arduino and an IR sensor, and it looks very similar to a paper that was published, and it's very possible that they're using that linear regression with the polynomials, which I don't think is the most accurate in the long run, but it's a quick way to get started. But that was sort of a tangent. What I wanted to get at here was that if I were to actually plot this value out, the polynomial I got was overfit to the small amount of data. So it actually like peaks, the highest blood glucose level it'll ever predict is right around here, right around 125. So it's very much a bad equation. And if you were to get more ranges of sensor readings, you would see that it gives you absolutely like incorrect values for blood glucose level. It'll never give you values up in this range. So the actual polynomial that I have is like this red line right here, where it's just, oh, sorry, I'm going a little off the screen. So it's like this red line right here, where it's not actually super, it's wrong. That's all there is to it. It's overfit and it's wrong. When in reality, you want something more like this green line going up through there. And it may not look exactly like this, but you want something that generally goes up with that kind of trend. You can't tell that this glucometer is wrong like that by looking at these numbers. Looking at any one of these numbers seems to give the impression that this is reasonably accurate. But you can't tell that it's not at all, that it's actually extremely inaccurate. One of the things, if you have this Clark's error grid analysis chart, you can look at it and you can get an idea of, okay, how many data points do they have? Do they really go through this range of concentrations? And if they do, okay, that's good. That's a good sign. But if you see something like this, that's like obviously like a huge red flag. Like, no, you're just looking at a very, very narrow region. That's not a good test. So I just wanted to share that. There's actually entire papers out on how these may not be the best values to use when describing accuracy alone. That's not to say that they're bad values. It's just to say that this alone doesn't give you the full context that you get with a chart like this. So that was just some interesting stuff. I'm also not trying to say that the prediction algorithm is terrible. I think that the issue with this prediction algorithm is the lack of data I have. The fact that I have a set of data that's in this very narrow region, and I have not figured out exactly how I'm going to get data in other parts of this region yet. I've tried to, I pushed myself pretty good to try to lower my blood sugar and to increase it. And I was a little surprised I couldn't do it more. That's probably good, that I didn't spike it too much. Like, that's probably a good thing. But it does really limit the range that I can test with, which is not ideal at all. And I haven't figured out a great solution for that. But that's why I also haven't shared a lot of the correlation data in here, is because I don't think that you can make any really strong calls right now as to its effectiveness or ineffectiveness until I get more data to evaluate it with. Yep. So, next steps. Get more data. This is a must to see the big picture correlations. So I've got to get more data. There is somebody who uses a continuous blood glucose monitor that I'm going to be loaning this to or giving this to, I'm not sure. But either way, I'll be giving it to them this weekend, and I guess they'll probably use it for 2 weeks to a month, and then I'll get this SD card back, and I'll try to use that data and post-process it and see if we get some stronger correlations or some interesting data there. I think the other big next step is feature extraction. Extracting key PPG data does not appear to be a major factor in correlations because I haven't extracted any. So I think developing that feature extraction would definitely be a major improvement. It seems like the most accurate non-invasive glucometers are doing that. So they are looking and I don't know all the terms for it yet, but they are looking at like the key features of these waves, like what's the average height, what's the average slope, width, width here and here, what's the slope here, distance, all those things. They're looking at those features and they're extracting them and looking at the variance between various window sizes. They might have a window of one pulse, or they might have a window of multiple pulses, or a partial pulse. So they shift those window sizes, and they tend to be putting those in machine learning models to get pretty accurate results and to improve the results that they're getting using this near infrared range light. So yeah, I think that would be the next step. And I think that would also be useful to other people to be able to share maybe a Python or a C library for extracting this data from signals. So I think that would be nice. Consider removing some of the sensors. So since I can see here that some of the sensors have not worked very well so far, and I will get more information on that as it gets used more. But maybe I decide that, okay, I don't actually want to measure the reflectance for the near infrared, or maybe I don't want to measure the transmittance for the red light. And by doing that, I can increase the sampling rate. So maybe I can go from 300 hertz to 400 or 500 hertz, and that'll give me more detailed information to analyze. So that's an option. I'm not set on it yet, but it's something to think about in the future. And also considering COT sensors and looking at what may be easier to create. I would like to spend more time to see if there's anything out there that either is using that near infrared range, or if it could be easily modified to. And when I first looked around, I didn't see anything that looked like what I wanted, but that doesn't mean it doesn't exist and I didn't just miss it. But yeah, so that is the big picture. And just so you can sort of see what I've been doing, I'm going to go ahead and do like one log right now. I'm not going to post-process it and analyze it, but I'm just going to show you how I've been using this. And you can sort of see, and if you have any comments, feel free to let me know if you think I'm missing something or there's a better way of doing it. So the first thing I've been doing, is I write down the actual true or the reference blood glucose just on a sheet of paper, and I've been keeping track of it that way. So what I'll do is I'll bring this out, and I've been using this Meteen TD4116 meter. I don't know very much about them. I think I got this on Amazon. It was, I think, relatively inexpensive. I want to say that this whole kit, if I remember correctly, was about $50, which interestingly is what this thing costs. This costs about $50 for all the parts to make as well. So that's kind of cool. And obviously, if you're going to mass manufacture this, you could definitely bring the price down, and you would change things up. So for $50, I do think that's a nice point about this, that I have managed to keep the costs down to build it. That's not too bad. So anyways, first thing I do is I will record the blood glucose level. Sorry, I haven't done this on camera before, so we'll see how it goes. So get that ready, and we'll put a little lance in this thing. Okay, so warning people, there's going to be blood that you will see. I don't know what the rules are with that. Hopefully, so yeah, this is your opportunity to stop the video if you don't want to see blood. It's just going to be a little bit, a teeny, itty bitty tiny bit, but just be aware. Okay, so, yep, do that. Get that little bit. Put that there. Okay, so 112. And what I've been doing is I've been taking multiple readings, because I've noticed that sometimes it shoots up and down. And so to get a better idea if that's the case, I've been taking 2 readings now. I'll just use the same site and just Try to push a little more out. Record it again. See if we get the same thing. Similar value. Okay, 104. Not too different there. Then I've been recording SpO2. I don't know if I would continue to do this because I haven't seen a lot of variation in this thing at all. So I really don't think that I'm not sure the usefulness in this, but I'm also not 100% it's not useful. So I've just been sort of roughly recording it. I record the highest and lowest value I see here. So I saw a 97 and a 96. I wait a few seconds and see what happens. And then I just record it and write it down. Not highly accurate there, but you get the idea. 7. Okay. Then I can connect this guy right here. Just power it in, power it on. This little micro USB. Pops open like that. Make sure the SD card's in there good. And then I hit B, which is going to be for logging after I get my finger in there. And the order I've been doing it is full index finger first. And I just hit B, and it starts recording, logging the data. You may see the lights turn off and on if I get a good view here. Go off. Let's see if I can get it where it's visible. I don't know if you saw that right there as it goes through. So I actually do this 4 times. Because I was originally wondering how it mattered where you put it on your finger and which finger you used. Okay, so there's log 1, or 81. And then I reset it. And the way I've been resetting it is you can hit this button right at the top there. It says it's ready again. I've adjusted it slightly so it's just over the nail. And then I record it again. So before I had it up here a little bit higher, closer to the knuckle. And this time I'm just doing it over the nail. And what I found is that so far, having it over the nail gave worse readings. It was better to keep the phototransistors above the skin, further up the finger. But I wasn't sure at first, and I still don't have a ton of data, so I'm not 100% sure. But so far, the initial data seems to show that yes, having it above the skin gives better results than having it above the nail. So there's log 82. Then I switch to the pinky, and there you can see I try to get it further down towards the knuckle, reset it, and have it start logging. I don't know if I actually need to reset it every time. I remember at one point there were some glitches when I tried to record multiple logs at the same time. I don't know if those glitches are still there or not, but I've just been sort of playing it safe and resetting it. It may be overkill and you don't actually need to do that, because I don't know that, I never figured out what exactly caused the glitch to say that I actually fixed it or not. So let this keep going. And I can see my hand moving a little bit right now, and so I can't help but wonder too, how much does that affect the readings? So then I do the fourth one, which is just above the pinky. Reset it, and then start logging again. And so I've been doing those 4 logs for each session or whatever. You can see it doesn't take too long to run. It is a little time consuming, but I'm trying to gather a good amount of data for it. So, yeah. So after this is done, then I just go back and I take the SpO2 again and the blood glucose readings again. Excuse me. Okay, so there we go. So we got 84. So I'm going to make a note. So 81, 82, 83, 84. And then I will record the SpO2 again. I don't know if you can hear. So we got 97. It's the 4th of July, so there's fireworks going off outside right now. 96 to 97. Okay, so I will write that down. And then I'll take another reading on here. Yep, another warning. You're going to see a little tiny bit of blood. Okay, so we'll see what it comes out to now. 114. I'll take one more log. And I'll try to get a little more out of there. And then I'll record that. Okay, so 105. Okay, and so that's basically how I do it, and that's how I've been recording it. And that's all this does right now. If you actually try to get it to estimate the levels, it just gives you a -1 to sort of been like, it doesn't work. I haven't built in any prediction algorithms into the sensor yet. I've been doing everything in post-processing, so afterwards I go on my computer, and at the moment I have a MATLAB script where I punch in these values, and I punch in the log, and it reads them into one massive log file that I also upload to GitHub, where you can see the details. Yeah, and then have been using MATLAB to do the estimation. I haven't gone through the effort of programming it in here because I haven't found an algorithm that's, super reliable yet. But that is the goal. And yeah, so this is the project I've been working on lately. I've been trying to make sure that I record enough details that people can recreate it. I know that there's a lot of research in this field, and one of the things I've noticed is that, and there's videos on it, there's videos on YouTube of people having non-invasive glucometers, but everybody's been sort of keeping a little bit of the secret sauce to themselves. They haven't been sharing all the details, which I understand that's fair. Like if you're a researcher, there's a lot of work that goes involved, and you may not want to give every single detail for somebody to sort of copy your work. But I think in the long run, it will be nice if we have like a reference or people can say, yes, I know exactly how to make something just like you did and get the same results. So that's sort of what I'm going with GitHub, is that it is hopefully that I will come up with a sensor that is completely reproducible by other people, and they can slightly tweak and adjust to compare the results. Like the idea with this even is that it's modular, so that you can unplug this. The code can be basically the same here, except maybe you change a few implementations slightly, but you can take a new sensor, plug it in, and continue to use this and minimize the amount of changes. So I've tried to keep the code modular. I've tried to use these modular components these are from Adafruit. They're not the cheapest. I think these are like about $10 or $15 each. So, not what you want for a commercial product, but for something that's modular and easy to change out. Okay, we don't like this screen. We want to use a different one. Okay, we want a board with more RAM. We can use a different one. So they're not perfect, but they have the advantages of being modular, and that is convenient for trying different things. So it's an option. It's not perfect for every scenario, but it's an option, and that's sort of what I've been going with so far. And also all the details, Adafruit shares all the details. I think they might call it an open hardware policy, but they have the schematics for all of these things online. So you could recreate this and turn this into, if you get something working just amazingly, you've made the massive breakthrough, you can convert all of that into your own dedicated board. All of this is open information as well, so you can very easily recreate, make your own PCB for your project or your commercial idea. Yeah, so that's it. I hope that is interesting to somebody out there. Yeah, and feel free to let me know what you think, for better or worse, in the comments. I know there's some people that I've read on some forums, some people like, that non-invasive technology just doesn't work. And if it did, you would see it out there already. And I also see papers where they seem to show it working. So there is some disconnect there. There's papers reporting decent results. And there's also catches. There's the catch that, you know, it can vary based on other things like medications. But I'll tell you what, I've seen some pretty big variations in this thing, this invasive glucometer. I've seen some pretty big spikes. I keep my notes on another sheet of paper, but I also kept notes for work, so I'm not going to show it. But basically, I've seen big spikes in this thing as well, which were very surprising and makes me question the accuracy of these commercial devices that are available out there. Not that it's necessarily so inaccurate that you would make a bad decision. I don't think that's the case. Just that this is not a highly accurate device either. From what I see, you see a pretty. You can easily see variations. You know, like we see here of, 8 milligrams. On this one, what do we've got? We've got 9, and I would say that those I've definitely seen. I want to say 25 milligram spikes between readings. Like, that's crazy. That shouldn't. I don't see why that seems like a huge spike to me, or a huge variation. But anyways, I'm going to stop rambling. This is already way too long. All right. Thanks for watching. Hopefully there's something useful to somebody out there. And yeah, thanks.